The ultrasonic transmission method is a detection method for determining the integrity of a pile body by emitting high-frequency elastic pulse waves from an ultrasonic pulse source concrete and recording the fluctuation characteristics of the pulse waves during propagation in the concrete using a high-precision receiving system. So, what exactly is the principle of ultrasonic transmission detection? What are the requirements and preparation work before testing? Below, let us proceed with this lesson's learning. First, we will study its detection principle. Pre-embed 2 in cast-in-place piles, or 2 or more sound measuring pipes as detection channels. Fill the tube with water as a coupling agent. Emit and receive acoustic waves between pre-embedded sound measuring pipes. By measuring the relative changes in acoustic parameters such as time t, frequency f, and amplitude a, attenuation of the sound waves propagating in the concrete medium. Detect pile defects. Suitable for integrity inspection of cast-in-place concrete piles with diameters not less than 800 millimeters. Below shows acoustic wave types and corresponding frequency ranges. Types of sound waves and their corresponding frequency ranges. As the name suggests, ultrasonic wave refers to a frequency that exceeds the audible range of human ears, as can be seen from the table. The main frequency used in concrete ultrasonic wave transmission method generally ranges from 2 multiplies the 4th power of 10 to the 10th power of 10 Hz. Here, what we need to note is, ultrasonic waves are mechanical waves. Mechanical waves are divided into transverse waves and longitudinal waves. Next, we study the wave velocity of acoustic waves in elastic solid media under different boundaries. Wave types include longitudinal wave P, transverse wave S, and surface wave R. Its expression is as follows. Under the same conditions when Poisson's ratio is can then be known. The wave velocity of longitudinal waves and greater than that of surface waves, and is greater than that of surface waves. For concrete piles, Poisson ratio, ultrasonic wave velocity approximately equals 1.1 times low strain wave velocity, combined with significant frequency dispersion and drift in low strain conditions. Therefore, the ultrasonic wave velocity is greater than the low strain wave velocity. Next, we study the propagation characteristics of ultrasonic waves in concrete defects. When ultrasonic waves encounter concrete defects during propagation, such as fractures, cracks, mud inclusions, and poor compactness, the following changes will occur. 1. Sound time, T. Sound velocity V. Acoustic waves must bypass defects or pass through media with slower propagation velocities, causing propagation time to increase. Sound velocity decreases. 2. Wave amplitude A. Concrete defects cause significant attenuation of acoustic wave amplitude. Waveform distortion. 3. Frequency F. Acoustic wave frequency changes. Main frequency decreases. Second, let's further understand 3 causes of energy attenuation during ultrasonic wave propagation in solid media. Diffusion attenuation. It is because the sound energy weakens as the propagation distance increases. Scattering attenuation. Due to scattering, part of the sound energy cannot continue along the original path. Absorption attenuation is due to internal friction in the medium. Part of the sound energy converts into thermal energy. Understood the detection principle, types of acoustic waves, and characteristics of acoustic wave propagation. Next, Let's learn about pile integrity testing using the ultrasonic transmission method. Instruments and equipment required and detection technology requirements. Acoustic wave instrument. By computer. High voltage emission and control. Programmable amplification and attenuation. A or D conversion and acquisition components. The working principle involves emitting sound wave pulses into the structural concrete being tested, then receiving the pulse signals transmitted through concrete, based on the time and distance of sound pulses traversing the concrete. Calculate propagation velocity. Wave amplitude can reflect the energy attenuation of sound pulses, based on the displayed waveform. After proper processing, spectral analysis can be performed on measured signals. Transducers are divided into emission transducers and receiving transducers. Emission transducer achieve the conversion of electrical energy to sound energy. Receiving transducer achieve the conversion of sound energy to electrical energy. Its technical requirements are as follows. First, non-directional along the radial direction, horizontal direction. The resonant frequency of the radial transducer should preferably be within the range of 20–60 kHz. The effective working surface axial length should not exceed 150 mm. 3. The measured main frequency should not deviate from the nominal frequency by more than plus or minus 10%. Its watertightness should not leak under 1 megapascal water pressure. Acoustic measurement pipe. Material requirements. Steel pipes, steel corrugated pipes, plastic pipes. The inner diameter should be 1 to 2 centimeters larger than the transducer diameter. Embedded quantity. Having understood relevant inspection equipment. Next, it requires us to conduct testing through hands-on practice. This is also the key point of this lesson. Please remember every step and procedure. And in future operations, strictly standardized operations. Preparation work before testing. Information to be collected before inspection. 1. Review technical documentation related to cast-in-place piles, including geological data, pile length, pile diameter, concrete design grade, and age. Construction conditions of cast-in-place piles. Presence of abnormalities, etc. 2. Record the design elevation of pile bottom and pile top. 3. Measure the elevation of sound measuring pipe openings and each pipe's bottom elevation. 4th, draw the orientation diagram of each sound measuring pipe. Preparation work before inspection. First, the concrete age of the inspected pile should be greater than 14 days. Concrete strength should not be less than 15 megapascals. 2. Sound measuring pipes should be filled with clean water and remains unobstructed. 3. Accurately measure the inner and outer diameters of sound measurement tubes and the distance between the outer walls of 2 adjacent sound measuring pipes. Measurement accuracy is plus or minus 1 mm. 4. Calibrate the system delay time T0 from reflection to reception of the ultrasonic testing instrument. Arrangement of sound measuring pipes starts from the vertex in the direction of root advancement. Numbering and grouping should follow a clockwise rotation direction. Every 2 pipes are grouped together. Detection steps. First, conduct a general survey using the flat measurement method. Identify measuring points with abnormal acoustic parameters. Then, adopt dense testing and oblique measurement or sector scanning methods for further detection. On one hand, it can verify survey results. On the other hand, the scope of abnormal locations can be further determined. Take flat measurement as an example. Step 1. Combine multiple sound measuring pipes into complete sets of 2 pipes per detection profile. Perform profile encoding. Step 2. Place the emission and receiving transducers in two sound measuring pipes of a given cross-section, and lower to the bottom of the pile. Maintain the same elevation. Step 3. From bottom to top, the transmitting and receiving transducers. Lift upward with the same step size, preferably not exceeding 100 millimeters. Each time it is lifted, conduct a test. Real-time display and recording of the time history curve of acoustic wave signals at measuring points. Read the sound time, first wave amplitude, and period value analog acoustic wave instrument. It is advisable to simultaneously display the spectrum curve and dominant frequency value digital instrument. The focus is on sound time and wave amplitude. Also pay attention to changes in the measured waveform. Step 4. During the detection process of each detection profile in the same pile, acoustic wave emission voltage and instrument setting parameters should remain unchanged. Sound velocity calculation by acoustic wave transmission method. Comprehensive judgment of pile body concrete defects. Comprehensive judgment method. 1. Sound velocity criterion. When the measured concrete sound velocity is lower than the sound velocity critical value, it should be considered as a suspected defect area. Sound velocity critical value. The difference between the average sound velocity of normal concrete and twice the standard deviation of sound velocity. 2. Wave amplitude criterion. Use the average wave amplitude -6 decibels as the wave amplitude critical value. When the measured wave amplitude is below the wave amplitude critical value, shall be identified as a suspected defect area. 3. PSD criteria. Adopting the slope method as an auxiliary anomaly criterion. When the PSD value changes significantly near a measuring point, shall be identified as a suspected defect area. In this lesson, we mainly studied ultrasonic transmission testing principle and embedding requirements for sound measuring pipes, as well as the relevant technical requirements for ultrasonic transmission method testing. Practice yields true knowledge. Hope to apply in future work. Everyone can focus on learning. Strive for excellence. Continuously improve one's technical skill level. Safeguarding engineering quality construction. After class, please consider the following questions. 1. Under what circumstances can foundation piles not be tested by ultrasonic transmission method? 2. During pile foundation inspection, why the wave velocities measured by acoustic wave transmission method and low strain reflection wave method differ?